Hi, greetings. Myself Dr. Gopal Reddy, and our today's topic is structures and bonding in metal carbonyls. How this metal atom will be coordinating with that of the carbonyl ligands, either by bombing the sigma bond or by percussion of pi bond and metal carbonyls are coordination complexes of transition metals with the carbon monoxide ligands. So this metal carbonyls, as name the terminology indicates, the metal atom is directly coordinating with the that of the carbonyl groups. So that carbonyl group is called as carbon monoxide. Metal carbonyls are useful in organic synthesis and as catalyst and catalytic precursors in homogeneous catalysis. This many of the metal carbonyls are used as a catalyst, either homogeneous or heterogeneous catalysis. We are using plenty examples are there. The carbon monoxide ligand may be bound terminally to a single metal atom or bridging to the two or more metal atoms. See this CO ligand, which is carbon monoxide ligand, is coordinating to the central metal atom either terminally. That means that the carbonyl group is present in the extreme end of the molecule, metal atom, or this carbon monoxide ligand will be acts a bridging between two or more metal centers. That I am going to discuss with a few examples later. These complexes may be homoleptic. Homoleptic, as homo means same. See, this is an example of homoleptic. So in this complex metacarbonyl compound, so all the four ligands will be of the same type. That is, all four ligands are carbonyl group. So then that kind of complex are called as homoleptic complexes that containing only one type of CO ligand, such as nickel tetracarbonyl. See, this is there are only one type of ligands are there. That means all four ligands are carbonyl group. So then such complexes are called as homoleptic. If but more commonly metal carbonyls are heteroleptic. Heteroleptic means so they contains a mixture of ligands was a pure carbonyl group, pure some other ligands. So such complexes are called as heteroleptic so complexes. In metal carbonyls, all the metals are neutral. So if you take any metal carbonyl compound, so in all carbonyl compounds, the metal will be acts as a neutral metal atom. So generally they will be in zero oxygen. So then, so this terminology called hapticity is also important here. So hapticity, the definition of hapticity is the number of ligands in that metal center is coordinating with the number of carbon atoms, or else the number of carbon atoms are coordinating to the central metal atom is defined as hapticity. So the hapticity is from N1 and eta 1, eta 2, eta 3 and so on. So eta 1 represent the monohapticity. That means one carbon atom is coordinating to the central metal atom. So here hapticity eta to the power of x. So eta represents the number of eta, that's bonding coordination, with x represents the number of carbon atoms. Example eta 1. So eta 1 means one carbon atom is coordinating to the central metal atom. So eta 2. So there are two carbon atoms, they are coordinating with the metal atom. Eta 4. There are 2 plus 2, so totally 4 carbon atoms are coordinating with the central metal atom. So eta 3, this is eta 3. There are 3 carbon atoms are coordinating with the central metal atom, eta 3. And eta 5, so there are 1, 2, 3, 4 and 5. So totally 5 carbon atoms are coordinating with the central metal atom. So then the hapticity is equal to 5. So hapticity, which represents the number of carbon atoms are coordinating to the central metal. When come to the structure and bonding in metal carbonyls, so generally what happen, the metal carbonyls exhibit both formation of sigma bond as well as the pi bond. So this is a sigma bond. When the sigma bond is formed, during sigma bond, this electron density will be flow from the ligand carbonyl to some metal atom. So in such case, the ligand will be having filled pi orbitals, and metal atom will be having empty d orbitals. Then what happened? The electron density is flow from ligand to metal atom. The charge transfer will take place from ligand to metal. So here ligand acts as donor and metal acts as an acceptor. So then as electron density is moving from the ligand to metal, so then the formation of sigma bond will be taking place between metal and the carbon atom. And all the metal carbonyl bond, sigma bond, always is a coordinate bond. So because the lone pair which is present on the carbonyl group, which is both the electrons are contributing the formation of the the bond. So hence all the bonds are formed as a coordinate bond. And once the electron density is moves from the ligand to metal atom, so the metal atom will become electron rich, because generally what we discussed in the previous slide, the metal atoms will be in zero oxidation state. Once the electron densities moves from carbon to the carbonyl group to the metal atom, the central metal atom become electron rich. To make it metal atom neutral, so the metal atom will start giving electron back to the carbonyl group. Once it is start giving the electron density back to the carbonyl group, the electrons are start filling the anti-bonding molecular orbital level, that is pi star anti-bonding. See example, see this is carbon atom, the carbonyl molecule, CO molecule. So once the electron density is coming from the metal atom, that electron will be going filled to the pi star anti-bonding level. See, once this electron will become to the start filling up to the pi star anti-bonding levels of the carbonyl group, then the bond order is equal to half into Nb minus Na. Nb means number of electrons present in the bonding molecular orbitals, minus Na, the number of electrons present in the anti-bonding molecular orbitals. So as the number of electrons are increasing these levels, will obviously cancelling the bond order between the carbon and the oxygen. See now here, when the sigma bond is forming, the triple bond is there between carbon and oxygen. And once the electron density moves from the metal to carbonyl, so then automatically the bond order decreases. So as bond order decreases from 3 to 2, and there will be two double bonds are forming, the pi bond is forming between the metal and the carbonyl group. So this is called as back donation. The back donation will be takes place when the filled d orbitals are present in the metal, and that electrons will move from the filled d pi orbitals to antibonding pi star orbitals of the carbonyl group. Then as the bond order decreases, the bond length also increases, because bond order and bond length will be inversely proportional. So triple bond, or the bond is very shorter. Double bond is little bit longer than the triple bond. So as bond order decreases, the bond length increases. That this was confirmed by the infrared spectroscopy, when we measure the stretching frequency, which indicates the here the stretching frequency is requires less compared to that of this one. See, these are the few examples of the metal carbonyls. So the metal carbonyls will be, we are obeying EAN rule. So here we are having chromium hexacarbonyl compound. So when you calculate the EAN rule, effective uh, atomic number, so EAN, so rule, so which will obeys the 18 electrons noble gas configuration. So central chromium will be having valence electrons are 6. That is outermost electrons 4s2 and 3d. So 4s1 and 3d pi. Total 6 electrons are there, and there are 6 carbonyl groups are there. So 6 into CO is, so each CO is contributing 2 electrons. 6 into CO is 12. So there are totally 12 electrons are there. So 6 plus 12 is so 18 electrons. So hence this molecule is so existing. Similarly, here we are having binuclear. Binuclear means there are two metal centers are there. So Mn, so metal, each metal atom is contributing 7 electrons. That is, atom Mn will be having atomic number 25. So 25, that means the valence electrons are 4s2 and 3d5. Totally 7 electrons are there. So you can take 7 plus 7, it is 14. And there are totally 10 carbonyl groups are there. So 10 carbonyl groups means it's contributing the so totally 20 electrons, and metal metal bond, so there will be a 2 electrons, so total it becoming 36. So there are two metal centers are there, hence 36 divided by 2, that will be gives the so 18. Either we can calculate for binuclear or mononuclear. Similarly, iron pentacarbonyl, which is obeying En rule. So cobalt twice CO8, that is also obeys this En rule, and that nickel tetracarbonyl so also obeys so that En rule. And here a few more examples. So mononuclear, binuclear, and polynuclear complexes. So mononuclear, you see this all are having one metal center, and all mononuclear carbonyls are exactly coincidence with that of the geometries with the coordination that number. So that mean here coordination number is 4. So coordination number 4 means generally they will be forming so tetrahedral geometry, so with the sp3 hybridization. And here coordination number is 5. So they'll generally they'll be forming trigonal bipyramidal, that is uh, 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 D sp3. So generally they're forming the trigonal bipyramidal geometry. And here see this coordination number is 6. These are forming the so octahedral geometry, so with the D2 sp3 hybridization. And here binuclear, some are binuclear means there are two metal centers are there. See, one carbonyl and one carbonyl, and these will be vary with the geometries. So geometry, this is see this each this carbonyl group so is forming trigonal bipyramidal, that is 1 2 3, these are forming the trigonal pyramid triangular shape, and this carbonyl and this cobalt will forming the so this will be occupies the equatorial, and this will be axial, so that this forms the trigonal bipyramidal, as well as this will also forming the trigonal bipyramidal. And this is a CO twice CO8. So and like got other examples of iron Fe, and here M, that is manganese, tellurium, and rhenium. And here we come to the other cases, the polynuclear. Polynuclear means there is more than two. So there are three iron centers are there. So metals where the ruthenium and osmium is given here. And similarly here cobalt and the rhodium, so iridium, and other few examples with the cobalt and so rhodium. So these are the few some examples of the metal carbonyls. So with the mononuclear, binuclear, and polynuclear. So when come to the characterization of metal carbonyls, so this the bonding which is present this with this metal centers, so it may be pre, that mean if you take CO alone, so that will be having exhibit the switching frequency of 2143, so in the IR spectroscopy. But when the this carbonyl group is coordinating to the central metal atom, so terminal means it will be present at the extreme end. So then see this, their switching frequency will be decreases. Why? Because as this will be pulling the electron density to this side, so then as it pulling the electron density to this side, this bond switching frequency, bond length become what increases. So as bond length become increases, so then what happen, so this can be easily stretched between the this range, so hence bond switching frequency is decreased. And then if it is a symmetric mu2, that means that is coordinating bridging between the two metal centers. So then what happened that time, even the decrease in the stretching frequency. And even if you go down simply mu3, that is mu indicates the bridging. So mu2 means it between the two metal centers, and if it is mu3 means it will be three metal centers. So these three metal centers are there here, and this stretching frequency even decreases because so this electron density of this carbonyl group will be shared between these three metal centers, which is pulling the electron density toward themselves, because as metals will be acts as an acids, so this ligand will be acts as an donor of electron pair, so that which will be forming the bonds with this central ligand, and decreases their stretching frequency. So here I given the range of their functional groups, that's the terminal carbonyl, so with the bridged carbonyl and mu3 carbonyl, that is with the cobalt as a carbonyl group, which is bridging between three metal centers. And these are the same examples what I discussed here. And here another important point we not to be, should note, has see you can when we see the change in the charge, because see these are almost all same. So MCO6, that is titanium CO6, vanadium CO6, chromium CO6, MnCO6, and iron CO6. So the only the change in the change you can observe here, the charge 2 minus, minus, 0 plus, and 2 plus. As you change, as the change in the charge, that means so the charge will be taking changes automatically. The stretching frequency also varies, because as the charge is varying on the central metal ion, so there will be the attraction between the ligands and the metal atom will be varies, hence the stretching frequency also changes. So lower the frequency and weaker the CO bond, that means as CO bond is too longer, so then stretching frequency requires very less. So and also similarly we see this that the variation in the effect of the ligands. See this MoCO3, 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 MoCO3. But if you see this changes in the ligands, PP3 thrice, PCl3 thrice, PClPH2 thrice, PME3 thrice. See, just by varying the ligands here, so there will be a change in the switching frequency. So here, so ligand the substitute presence of other ligands also will affect the switching frequency, as well as the charge on the so metal complexes also will affect the so switching frequency complexes of the, and here p bonds, that mean whether the stretching will be taking place symmetrically or asymmetrically. See, symmetrically means what? See, with respect to this metal atom, so this CO is stretching in this CO is stretching either compression or elongation. So compression means both should be having same compression. This also. Or expansion means this also should go expand, and this also should go expand. That's called symmetric. Both should be happen same. And here when we see this is actually undergoing for compression. See, this is undergoing for compression, this is undergoing for li extension. So such can there will be different types of stretching modes are there here. So as we see this different types of stretching modes, so we can get the different types of, and here the few examples of the metal carbonates are there. So with their state and their magnetic nature and their melting points, so which are given here. So vanadium hexacarbonyl group and chromium hexacarbonyl likewise. See, now iron is exist in both mononuclear, binuclear, and trinuclear, called as a polynuclear. And similarly the cobalt, so these are the first row metal centers. Second row metal centers are molybdenum, tellurium, ruthenium, rhodium complexes, and third row, that is tungsten, rhenium, osmium, iridium. So these are the familiar metal carbonyls, so are existing either in being mononuclear or binuclear or in the polynuclear so form. Okay, thank you.